Hello everyone, my name is Jiazheng Wang. Welcome to my exploration of discrete forward transform windowing. This technique is a cornerstone in the field of digital signal processing. Let's start by understanding the DFT. It's a mathematical technique that transforms a signal from the time domain, where it's a function of time, into the frequency domain, where it's a function of frequency. The results of DFT provides the frequency spectrum of the signal, revealing the amplitude and the phase of its sinusoidal components. DFT windowing is a process that involves applying a window function to the time domain signal before performing the DFT to reduce spectral leakage. Let's move on to our third slide, fundamentals of DFT windowing. This slide showcases the practical application of DFT windowing on a simple sinusoidal signal. We will examine how a window function affects both the time domain and the frequency domain representations. In our first plot, we have the original time domain signal, a sine wave at 5 Hz. This is our test signal, which we will be using to understand the effects of windowing. The second plot is the magnitude spectrum of our original signal after applying the DFT. It reveals a single peak at 5 Hz, which corresponds to the frequency of our sine wave. This is what we expect from a pure frequency in the absence of windowing. In the third plot, we see the effect of applying a Harming window to our signal in the time domain. Notice how the signal gracefully tapers off at the end. This window function is designed to reduce the abrupt changes that can lead to spectral leakage. Lastly, the fourth plot shows the frequency domain of our windowed signal. Observe the reducing in spectral leakage compared to the original DFT. The window function has helped to localize the frequency components, providing a clearer and more accurate representation. Let's explore the operational mechanics behind the DFT windowing and how it effectively addresses spectral leakage. We'll see how the application of a window function to a time domain signal before performing the DFT can enhance our frequency domain analysis. This is the coding. We have created the full fixture before. This code snippet beginning by generating a sine wave signal, then it applies a Harming window to taper the signal's start and end. We perform the DFT on both the original and the windowed signal to observe the differences. Notice the Harming function. This is where we define our window. The windowing is executed by element with multiplications of the signal with the window, which is shown in the code as windowed signal equals signal point time window. The plots generated from this code will show you the stark contrast between the original signal's frequency domain and that of the windowed signal. In the windowed signal's plot, you will notice less spreading of energy across frequencies, which is our goal in reducing spectral leakage. As we have seen, DFT windowing is a crucial step in signal analysis. It addresses the issue of spectral leakage that occurs due to the finite nature of real-world signals. By applying a window function, we effectively minimize this leakage, resulting in a clearer and more accurate frequency spectrum. In conclusion, DFT windowing enriches our toolkit for signal analysis, providing us with a more faithful representation of signals. Thank you so much for you watching the video, and thank you for your time.